In this section, we're going to look at several other groups of identities or formulas, and we're going to work with them. The first group is called double angle formulas, and here they are. It's a sine of 2 times some angle, you see, and cosine of 2 times some angle, tangent of 2 times some angle. Notice that cosine 2 times u has 3 different versions we can choose from. And that's rather interesting, because in some situations we'll want one of these and not the other two, as we'll see in just a moment. Now, all of these can be derived from, well, the second two can easily be derived from the first one, so you really only need to remember one, and then you can derive the other two as you need them. And the way they're derived is like this. You think of cosine squared u minus sine squared u. All right, that one, if we remember that one, then we can replace this with, now using the Pythagorean identity, we can think of this as 1 minus cosine squared, you see. And 1 minus cosine squared, with a minus sign right here, that's minus 1 plus cosine squared. Cosine squared, that's 2 cosine squared minus 1. You see, we've just derived this one from that one by using that little replacement. And if we use the replacement on cosine squared, we would get the other one. Okay, so that's the idea. At any rate, it's just the notion of looking at them, recognizing them, and then using them in certain situations, and then they will become familiar. The important thing here, I think, is not to become intimidated by all of this stuff. These are just formulas, you know, and you've used formulas many, many times in the past. And so just kind of refer to them and make use of them without trying to memorize anything. If anything is to be remembered, then the memory will come by great use, and not by sitting down and going through a memorization process. Okay, consider this problem. Now suppose we're talking about x in the interval from 0 to 2 pi, and we want to find the zeros of this function. Now the zeros, the place where the graph crosses the x-axis, zeros of factors, all of that comes into play here. Now, for the zeros of this function, we just set h of x equal to 0 and solve this. And to solve it, since we see that we have a double angle situation here, we refer to our list of double angle formulas. Now, one thing we need to do here is choose rather wisely the version of cosine 2x that we want. Remember that there are 3 versions. And if we look at the 3 versions and we look at what we have here, we might decide, well, you know, the prudent thing to do if we're going to be finding factors of this expression, and that's what we're trying to do here, is to rewrite this using only one ratio. And we'd like that ratio to correspond with this. So let's go back and choose the one involving only cosine. So we'd slide back over here. No, that involves cosine and sine. Oh, this one involves only cosine, that one involves only sine. Let's use this one. You see, that's how you make the decision about this kind of stuff. All right, so we're going to use this in place of cosine 2x. And so I'm going to write 0 equals, now instead of cosine 2x, I can use the formula 2 cosine squared x minus 1. All right, and then this is minus cosine x. And now we have an expression which is quadratic in form, so we'll rewrite it in the normal way, that is 2 cosine squared x, then minus cosine x, and then minus 1. And now we want to factor 2 cosine x, and then times cosine x to give that first term. And then the signs are different, and I think the way it goes is plus 1 minus 1. Let's verify the middle term. We have 2 cosine x times minus 1 is minus 2 cosine x, plus cosine x is minus 1 cosine x. That's the middle term, so this is the correct factored form. Now we want the zeros of the 2 factors, so we set them equal to 0 and solve them. That is, we're asking ourselves what value of x will cause 2 cosine x plus 1 to be equal to 0. And we go through that little process. Now recall that we'll kick the 1 to the other side and divide by 2. And I'm running out of room at the bottom of the board here, so I'm going to consolidate 2 steps. This is minus 1/2. And now we're going to evaluate this. Let's go over and solve this one right quick. We have cosine x, then minus 1 equals 0, or cosine x equals 1. Okay, for this one, well, let's see. Cosine x is negative 1/2. Well, I need some more information here. I need to go to that 1, 2, the square root of 3. I'm talking about cosine, so it's adjacent over hypotenuse. Oh, that's this angle. It's 60 degrees or pi over 3. So we're thinking pi over 3. Now we go to the idea of the coordinate plane, and we're talking about cosine here. Now cosine is positive in these two quadrants and negative in these two, so we're talking about a reference angle of pi over 3 that appears in these two quadrants. So we're talking pi over 3 in this quadrant, pi over 3 in this quadrant. All right, and now we're just asking ourselves what is this angle, and then what is this angle? See, that's all we're after. All right, if this is a reference angle of pi over 3, this is 3 pi over 3 at pi. It's 3 pi over 3 minus 1 pi over 3. That's 2 pi over 3. So this is an angle of 2 pi over 3. X then, I'll put them down here. X is 2 pi over 3. And then this one is 2 pi over 3, 3 pi over 3, 4 pi over 3. So that angle is 4 pi over 3. Now, for the other one, for the cosine x is equal to 1, well, gee, the cosine curve is at the top of its amplitude at the beginning of the cycle and at the end of the cycle. So x needs to either be 0 or 2 pi. Now, let's look back at our restrictions up here. Now, I breezed through this real quick, and I should have emphasized it a little more. X is between 0 and 2 pi, but notice that this says x is strictly less than 2 pi. So we can't use 2 pi in our list of values for x, but we can use 0. So adding to our list of solutions here, we would include 0. So these are then the 3 zeros for our function as requested. Here's another one. Now again, let's talk about finding the zeros of the function and using the techniques that we're talking about here. Also, we're restricting the value of t for values between 0 and 2 pi, but not including 2 pi. All right, so we begin by going 0 equals sine 4t and so on. Now, gee, I'm looking at that 4t and I'm wondering how in the world, we don't have a formula for that, but here's what we do. We let a letter like n stand in for 2t. Now, if we do that, then we can think of this as sine 2 times n. You see, n is 2t, so this can be thought of as 2 times 2t, but 2t is n, so it's 2 times n. And this is 2 sine, well, if n is 2t, then that's n. You see, so that's the idea. Now, we'll back substitute in just a minute, but looking at it like this allows us to use our double angle formula. So this becomes, now let's see, I'm having to refer back to it. I'm just going to look back over there and see what it is. And that's what you're going to have to do too. When you first use these, just refer back to some kind of chart or some place in your book and just write the formula down. It's 2 times sine times cosine. So it's sine n cosine n plus 2 sine n. Now, I wonder if I can get some mileage out of the algebra within this before I even go back and substitute for the 2t and the n business. Now, I'm noticing here that I have sine n here, excuse me, I have 2 sine n here, and I have 2 sine n over here. So I can actually factor 2 sine n from both of those terms. So 2 sine n times cosine n plus 1. You see, when I pull 2 sine n out of this term, I'm left with cosine n. When I pull 2 sine n out of this term, I'm left with simply 1. Oh, wow, that's convenient. Now, maybe it's time at this point for us to go back and do the back substitution and put the double angle idea back in here. Let's do that. We have 0 equals 2 sine 2t times cosine 2t plus 1. All right, now we have another substitution thing to go through. So 0 equals 2. Now sine 2t, again we're using the double angle formula for sine. So it's 2 sine cosine. Remember, it's sine t cosine t. And then this business is cosine 2t plus 1. Wow. You know, when I finish with all of this, when I manipulate this down, I sure would like to have a string of factors here that I can just look at. And I want those factors in the simplest form possible. So when I go and choose the cosine 2t replacement, the double angle replacement here, I'm going to try to look for something that will eliminate the 1 if I can. And it probably doesn't make any difference. We can manipulate our way out of it probably if we choose one of the other two. But if I have my choices, and I do, then I'd like to cause the 1 to go out. So let's slide back over here. Come on back over here with me and let's look at these 3. So if I'm looking at these 3, I have a 1 involved here and a minus 1 involved here. So I'm going to use this version of the double angle for cosine. All right, so here we go. Now, the letter involved over there is t, so it'll be 2 cosine squared t minus 1. Let's go over there. 2 cosine squared t minus 1 is the identity for this, or the formula, and then this plus 1 comes down. And then the 1's go out, and that's what we wanted to have happen here. So those are out of here. So now we have all of this business. Let's just clean this up. Now I'm going to just consolidate right here in the interest of time and space. I have 2 times 2 times 2. That's 8. And I have sine t cosine squared t. How many factors of cosine t do I have? I have 2 of them here, another one here. So this is cosine cubed t. Okay, now I have a consolidated situation which I can deal with in evaluating. Now, the idea is that I want the value of t that will cause each factor to become 0. Is there any value of t that will cause 8 to become 0? No. 8's just dead weight here. We can just kind of throw it out. Now, sine t equals 0. See, I'm really thinking in terms of, and I need a little space here. Let me back up over here and make sure we understand what we're trying to do. In this factored form, we are trying to find the values of t that will cause each factor to become 0. And what's down there is 0 equals 8 sine t cosine cubed t. Okay, we said that this makes no difference. And now we're looking for the values of t that'll make sine t equal to 0, and the values of t that'll cause cosine cubed t to be equal to 0. So we're solving these two. And both of them are fairly easy. The sine of what angle is equal to 0? Well, we're just thinking of the sine curve, and where on the sine curve do we have x-intercepts? Well, let's see. We have x-intercepts, and without even drawing it at some point, we ought to be able to imagine how that sine curve goes. It starts at an intercept. It starts at 0. It goes to the top of the amplitude and back through 0. You see, so it starts at 0, goes to the top of the amplitude, back through 0 at pi, bottom of the amplitude, and then back to 0. But that last 0 occurs at 2 pi, and we're disallowing that value. Okay, so 0 and pi for this. All right, now, what about cosine cubed t? Now, understand that, that in solving this is cosine t all cubed, so I can sort of take the cube root on both sides. So this is equivalent to having cosine t equals 0. Okay, now we want the angles which have a cosine. Cosine of what angles would be 0? Well, think about the cosine curve. The cosine curve starts at the top of the amplitude. Then we have a 0 at pi over 2. And then we go to the bottom of the amplitude at pi, and then we're back up at a 0 at 3 pi over 2. Now, if you're not recalling these things as I am talking about them, then it's worthwhile to construct the graph of the cosine curve and actually look for these actively on that curve. So anyway, we have solutions, we think, at 0, pi, pi over 2, and 3 pi over 2. Let's use the calculator to verify those solutions. The equation has already been entered, and I have made some window settings. Negative 0.5 for the x minimum, 2 pi for x max. The x scale should be set so that we can see our solution points easily. All of our solution points are multiples of pi over 2, so I'm going to set the scale at pi divided by 2, and the y minimum negative 3, y max 3, and here's what the graph looks like. I want you to notice how the graph appears to flatten right here where it goes through the x-axis, and here again as it goes through the x-axis. So it's maybe a little difficult to see that these are indeed solution points. We'll do something about that in just a moment, but we know here at 0 that's a solution point, so that's verified. Our x scale was pi over 2, so this is a distance of pi over 2, so that point is pi over 2. That was another of our solution points. This is another distance of pi over 2, so this whole distance is 2 pi over 2, or simply pi. So there's the position for pi. And here's another pi over 2, so we have 3 pi over 2 for that point. And notice we have a crossing here at 2 pi, but that was out of our domain and doesn't really count here. All right, to take a little bit closer view of this point of intersection, what we can do is reset our y maximum and minimum, and we're going to do that and sort of magnify this portion of the coordinate plane. We're just going to come in tight like this, and it'll cause the graph to look a little more vertical in that region. Here's what I'm talking about. I'm thinking of a y minimum at negative 0.5 and a max of 0.5. And now notice that the graph does not lay down or get flat as much at those points. And that's just a technique that you can use from time to time when you fall into a dilemma like this. In this problem, we're told that the tangent of an angle u is 1/2, and we're also told that u is between pi and 3 pi over 2. Now, this information simply puts the angle into the third quadrant. So we have a third quadrant angle. You see, it's this angle which has a reference angle in here, which causes a tangent of 1/2 to emerge. So we have a reference triangle like this, and we can think of, let's see, opposite over adjacent. So this would be 1 and that would be 2, but since we're in the third quadrant, they're both actually negative. Now, let's calculate from this information. Let's calculate sine 2u, cosine 2u, and tangent 2u. Well, we're going to use our formulas for each of these, but it's going to be handy for us to find the value of this hypotenuse. Now, it's c squared, you see, is a squared plus b squared. So we're talking about an a squared and b squared of negative 2 squared, negative 1 squared. That's 4, that's 1. So 5, c squared is 5, c then is the square root of 5. So square root of 5 for this. Now, for sine 2u, I refer back to the formula over there, and the double angle formula. So it's 2 sine u cosine u. And now I'm just referring to the triangle. So I have 2 sine u from the perspective of this side, opposite over hypotenuse, is negative 1 over the square root of 5. And then for cosine, it is adjacent over hypotenuse, so that's negative 2 over the square root of 5. And so I just evaluate this. With 2 minus signs and factors, I know we're going to get a positive result. So we have 2 times 2, 4, over the square root of 25. So this becomes 4/5. Now, for cosine 2u, I have 3 options. I can choose one of 3 double angle formulas here to replace. I think I'll choose the one that has only one ratio involved in it, so I don't have to evaluate more than one ratio. Well, okay, let's do that. I'm going to just look back over there. I'm seeing the one involving, let's say sine. It is 1 minus 2 sine squared u. All right, and away we go. Now, we understand this, excuse me, to mean sine u all squared. That's the way we need to think about it when we plug in, because it's 1 minus 2 times, now what is sine u? Well, again, we look back over here and the sine of this angle opposite over hypotenuse. So it's negative 1 over root 5. So negative 1 over the square root of 5, and all of this is squared. And now it's a matter of evaluating. And we can just about think our way through it. When we square the negative, it's going to be positive. When we square the 1, it's going to be 1. And when we square the square root of 5, it's going to be 5. So this is just 1/5. Now, 1/5 times 2 is 2/5. You see, so this is 1 minus 2/5. I'll write that down. So 5/5 minus 2/5 is 3/5. So 3/5 for cosine 2u. Now for tangent 2u, same idea. We just go to the formula, and I'm looking back over there. I know it's a fraction. 2 tangent u over binomial. 1 minus tangent squared u. And let's see, 2 tangent u. So 2. Now tangent u was given at the get-go of the problem. So it was 1/2. So this is 2 times 1/2. And over 1 minus, now this is just 1/2 squared. You see, because tangent u was given as 1/2. So let's see, this is just 1 in the numerator. And in the denominator we have 1/2 squared is 1/4. 1 minus 1/4 is 3/4. And 1 divided by 3/4 is 1 times 4/3, or simply 4/3. So 4/3 then for the tangent of 2u. There are several other groups of formulas that we want to have a look at now. They come in various categories: power-reducing formulas, half-angle formulas, product-to-sum formulas, sum-to-product formulas. They're written in your textbook. We're not going to look at every one of them up here, and I invite you just to kind of go over them and use them as reference. Now, we're going to just consider a few problems involving these in just a moment, but they're useful in simplifying certain expressions and in solving equations, as we'll see. Now, understand, though, the purpose of having these formulas, which can also be thought of as identities, but power-reducing formulas. Now, that means that we have a sort of a higher power and we want to reduce the power involved in our trig function. Half-angle formulas, we use these just like the double-angle formulas. Product-to-sum. It's as though we have a product, we're looking at a product and we want to express this as a sum. Here, sum to product. We have the sum of two items, that is the sine of one angle plus the sine of another angle, and we want the product of a couple of items. And there's a particular purpose for going through and using formulas such as these. Well, let's take a few examples. Now, again, I want you to think about these formulas as reference and just look at them in the textbook. Look at where you can find them. Look at the examples that are in your textbook and how these are useful. And then just use the list as reference. Okay, for this one, for sine 165 degrees, let's say we want an exact value for this. So we try to use double angle or half angle ideas in simplifying sine of 165 degrees. With a little investigation, we find that if we double 165 degrees, it turns out to be 330 degrees. And 330 degrees is one of those handy angles that has a reference angle of 30 degrees. So we're going to use a half angle formula. And the one we're using involves sine, of course. So it's sine u over 2, you see, is equal to, and I'm just taking this right out of the list, you see, and fitting the pattern for this formula using this particular problem. And that's what this study is all about. So here's the pattern that we want to match, and we want to match the pattern using this particular problem. So we're writing 165 degrees as 330 degrees over 2. And now we can use this half angle formula for sine. And all we're doing now is, now notice that in the formula, in this expression, we have cosine u, and u is the value in this numerator. And so here, to use it in this specific problem, it's the cosine of 330 degrees. Right? And everything else is brought down just as we see it. And now it's just a matter of evaluation, and it's pretty easy. Cosine of 330 degrees, we have a reference angle of 30 degrees. It's in the fourth quadrant. Cosine is positive in the fourth quadrant. Turns out to be the square root of 3 over 2. So just filling in, it's a pretty simple matter to fill in and analyze that situation. And now it's a matter of algebraic cleanup. Now we see a complex fraction situation here, and I think the easiest way to deal with it is to just take the common denominator of all small fractions in both this big numerator and big denominator and multiply that common denominator times both the numerator and denominator. That is, here we're multiplying by 2 over 2. You see, when we multiply 2 times the 1 up here, we get 2. 2 times this fraction, the 2's go out, and we have the square root of 3. 2 times 2 is 4 in the denominator. Now we can think of applying the radical to the numerator and denominator separately. We can't resolve the situation in the numerator, but we can certainly resolve the situation in the denominator. The square root of 4 gives 2. Now let's talk about the sign pattern here. This plus or minus value is just in here to choose the one appropriate for your problem. That's the idea. And appropriate for our problem. Now, although we used, within this problem, we used an angle of 330 degrees. You see, that's not the one that we're trying to find the sine of. We're trying to find the sine of 330 degrees over 2. That is, the sine of 165 degrees. And an angle of 165 degrees falls into the second quadrant. And the sine of an angle in the second quadrant is plus. So we would be choosing then this plus value here. So it's that fraction. Here's a situation where we can use a formula to help us solve an equation. Now, we see this, when you first look at an equation like this, just analyze it kind of like this. We have two different ratios involved. All right, now, one thing that we want to do is rewrite in terms of one ratio only. All right, that's one thing. Also, we have this half angle idea over here, so we want to get rid of that if we can. Well, we can certainly do that rather easily by using the half angle formula. Now, we're applying it here with cosine squared x over 2. And remember that cosine squared x over 2 means the cosine of x over 2 all squared. So we're just thinking cosine x over 2, using the half angle formula for cosine, it's plus or minus 1 plus cosine x over 2. You see, the x, this value is the numerator of that fraction. And that's all there is to it. So we apply the formula. Now, this squaring operation here is outside of the parenthesis when we write it in this form. And then I'll take it one more step before we even look at the other side. But plus or minus, when we square, we get plus. And when we square the radical disappears. And so we have simply 1 plus cosine x over 2 here as this part of the problem, as this factor, and when we multiply times 2, the 2's go out. So we have 1 plus cosine x. Well, that's rather nice. And then we look at the two sides of the equation and we think, well, how can we rewrite this so that we're dealing with only one ratio? We can do that pretty easily by taking the sine squared x and rewriting as 1 minus cosine squared x, using that primary Pythagorean identity. All right, and then we just resolve this situation. We're noticing here right away, though, that we have a quadratic situation, so that we're going to probably solve by factoring. At any rate, we have, let's see, minus 1 plus cosine squared x. And then I'm also moving these terms away from, just clearing them from the right side. So I'm subtracting 1 on both sides, and I'm subtracting cosine x on both sides to accomplish that. And now we just clean up here. I'm writing the term of highest degree first, and then the first degree term, which is minus cosine x. And then a really nice thing happens. 2 minus 1 is 1, and then 1 minus 1, they go out. So we have simply this. Factoring, we take out the common factor of cosine x. Take cosine x out of this term, we're left with cosine x. Cosine x out of this term leaves minus 1. And now off we go with analyzing these two factors. Once we're in a factored form, and that's what we're kind of driving at in all of these kinds of problems. Suppose once we arrive at that factored form, we can then say, we'd like to know the value of x that will cause each of the factors to become 0. So we go like this. Now let me backtrack over here because I'm just about out of room at the bottom of the board there. So I have this factored form. I'm just repeating the bottom step here. And now I'd like to know the value of x that will cause cosine x to be equal to 0. And I didn't mention it before, but let's assume here that we're going through one period here from 0 to 2 pi, and let's not include the 2 pi. So the x that we're looking for here is between 0 and 2 pi, but not including the 2 pi. All right, now, and in a similar way, we just take this factor and set it equal to 0, take the other factor, set it equal to 0, and then deal with them as sort of like separate problems. Now, the cosine of what angle is equal to 0? Well, we imagine the cosine curve. So we think in terms of, well, let's see, the cosine curve. Now, cosine of what angle is equal to 0? Well, that would be the angle at these points. Now, we know this to be pi. This is pi over 2. This is 3 pi over 2. So x then needs to be pi over 2, or x is 3 pi over 2. Now, for the other one, it's a similar kind of analysis. It is that the cosine x equals 1, and now the cosine of what angle is equal to 1? Well, let's see. Again, we kind of look at the curve here, and we're seeing that we're at the top of the amplitude here at an x of 0. So x needs to be 0 for this to take place. It also occurs at 2 pi, but we're disallowing that value because we're kind of back where we start from, you see, in this complete cycle idea. So our three answers are pi over 2, 3 pi over 2, and an x of 0. Here's another equation we want to solve. Now, notice we have the sine of some angle here plus the sine of another angle here. And we'd like to create a situation where we have factors involved. If we can look at a factored form on one side of an equation, then we can set each factor equal to 0. So the idea is to try to take this sum of two items involving sine and rewrite as a product. Well, that's the idea of sum to product, you see. And so we're going to use this identity. It's the sine of one angle plus the sine of another angle is equal to this product, 2 times sine of and cosine of, and we just kind of follow our way through this. We have a guideline here. It's just a formula, so we're going to fill in. So we have, let's see, we're just applying this idea, this formula, to this expression. Now, and notice, it's the x and y are the 6x and 2x involved up here. So we just fill in for those. So it's 2 times sine of the sum of the two angles in the numerator. Well, it's 6x plus 2x, you see, over 2. That's why I have this here. And then for cosine, it's cosine of the difference of the two angles. Well, that's 6x minus 2x, you see, over 2. So 6x minus 2x over 2. And now it's just a matter of simplifying a bit. 6x and 2x, that's 8x over 2 is 4x. And now 6x minus 2x over 2, 6x minus 2x, that's 4x over 2 is 2x. So now we go into this idea of a factored form, and so we set each factor equal to 0. Now the 2 doesn't contribute anything to our list of solutions, but certainly the other two do. Sine 4x then is equal to 0, and we like the values of x that will cause this to be true. Same idea with cosine 2x. We set it equal to 0. We ask ourselves what values of x will cause that to be true. And we do have to consider the notion that if we're thinking about x as lying between 0 and 2 pi, then we have to consider where 4x would lie in 2x in terms of the evaluation of each of these separately. So, well, let's see. If 4x, to consider 4x, we think, well, if we want x to lie between 0 and 2 pi, and notice that this is a strict inequality here, then I'll multiply in all parts by 4 to understand that my cycle here for this analysis is between 0 and 8 pi. You see, and for the other one, for the cosine of 2x, it's between 0 and 4 pi. All right, so we come back over here and we think about it like this. We think, well, the sine of some angle is equal to 0. And we then immediately go into the idea of the sine curve. All right, so we think this way. We think, well, the sine curve behaves like this. And we know this position to be pi, and here's 2 pi, and here's 0. Okay, so we have zeros for angles of 0, pi, and 2 pi. So 0, pi, and 2 pi make this true. But we have to extend this out several cycles. We have to extend it out to 8 pi. What we're noticing about the pattern, though, is that at the end of every pi length interval, we have another 0. So we have 0 and then pi, 2 pi. There'll be another one at 3 pi, 4 pi, 5 pi, and so on. So all the way out to 8 pi. But 8 pi is not included in this group of solutions. We said that we go up to, but not including the 8 pi. So we go up to 7 pi. And then it's a matter of saying, well, gee, if 4x, if the angle we're talking about here, you see, this is the angle whose sine is equal to 0, and we're finding those angles here. But it's 4x that we're finding. To find x, we need to divide through by 4, and dividing each of these by 4, we get various solutions to our equation. In a similar way, we analyze the situation for cosine 2x. Now, for the cosine curve, we think, well, for what values is this true? That cosine of the angle is equal to 0, and the angle happens to be 2x. So 2x takes on values of, and then we look at the cosine curve, and it turns out to be pi over 2, 3 pi over 2, 5 pi over 2, and 7 pi over 2. And, well, let me show it to you just to make sure we understand how that comes about. You see, we look at a cycle of the cosine curve, and here's the pi over 2 and 3 pi over 2. And then we go through 2 cycles of this. You see, it's pi over 2, 3 pi over 2, 5 pi over 2, and 7 pi over 2. Okay, so that's the idea. Now that's 2x though. 2x takes on these values. So what would x take on? Well, take half on both sides. Half of pi over 2, pi over 4. Half of this, 3 pi over 4. Half of this, 5 pi over 4. You know, these are starting to look rather familiar. If you look at these items, they are all items that are contained in this big list of solutions over here. So it turns out that this then is the complete list of our solutions. Now, if you look at the pattern here in terms of common denominator, that'll help us here with what we're going to do next, which is to look at it on the graphing calculator. This can be thought of as 0 over 4. But this is pi over 4, this is 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4. You see, all of these are just various values of pi over 4 for all of these. Now let's look at it and verify the idea on the calculator. The equation is in place, sine 6x plus sine 2x, and here are the window settings in case you're doing this along with me. The x minimum is set at negative 0.3 so that we can see the distinct x-intercept at 0. X max is 6.28, this is 2 pi. The scale, the x scale, has been set at this decimal. Now I entered this as pi over 4. Because we'd like to see increments of pi over 4 along the x-axis because that's where we're expecting the intercepts to fall. The y minimum is negative 2, y max of 2. And here comes the graph. 0, pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, and 8 pi. The 8 pi over 4 doesn't count because that's nothing but 2 pi and that's not part of our domain. So these are the expected x-intercepts that we found earlier algebraically.